Alright, so what we're going to do here is we're going to take working code and use it to look at different differential equations. Now I've included this code up on Canvas, and it's working to do, well, what does it do here? It prints the direction fields and the solution curves to this differential equation. Y times y minus 1 times 2 minus y. And what we want to do is we want to adapt this to be a little more flexible. And so I have a minimum of x, a max x steps, minimum of y steps. And so if I need to change things around, I can change some things in different spaces. So first, let's turn off the solutions. And we turn things off by putting a pound in front of it. So we're just going to turn off the solution area here. And what I know is in the future I can have multiple solutions now, because I have this solution section in the code. And if I need to turn it on, I just remove the comments. So let's make sure my code's still working. I just have a direction field. Nice. All right, so I want to come up and I want to change the differential equation and get a different direction field. So now notice my independent variable is x and my dependent variable is y. So I have to be careful when I look at certain differential equations. In fact, the one I'm going to look at in the book is dx dt equals t cubed minus x cubed. Now I'm going to, oops, I hit the shift enter, but that didn't change anything because that was a comment. So I'm leaving a comment of what my code would be. In fact, I am going to recast this in dy dx. And so wherever I see, I look here and I see wherever I saw x, I put in a y, and wherever I saw t, I put in an x. So this should be x cubed minus y cubed. Right? Just keeping track of my variables. And so what I want to do is use the power function in numpy power. Right? We used that down here when we had to do a power. And I'm going to give it the power because of, what is it, x, comma 3 minus numpy power y, comma 3. Now the reason we use the power functions is because numpy's passing arrays to these, and we need the array output. And look, I have my direction field. It's a pretty weird looking direction field, and I might want to explore it here. Definitely looks like things are flowing up. Right? There's some behavior happening around here in this rising line. In fact, it's linear in the cubics, so, and this line seems to be a line about, right, this line I'm seeing here seems to be around the line of y equals x. And so these cubic solutions are lying around that line. Well, let's see what happens when I look above and below the x and y axes. So I'm going to I'm doubling the size of where I'm looking, so I'm changing the size of my graph. Now notice I'm playing here now. I've got my direction field and I just want to look a little bit bigger in space. I'm not answering a particular problem, and I'm using code I had working to look. Well, man, that's really, really small, so let's bring these down here and see if that helps. Yeah. And so if I look across all of space, that pattern I saw up here kind of falls apart when our values are less than 1, absolute values are less than 1, and it picks up again on the negative side. So notice how I'm using my software to get behavior from differential equations, and I'm not rewriting the program. Taking the program I already used, and I have my new differential equations with it. So let me find a solution. So I'm going to need to turn on a solution, and I'm going to want to have it go for right now, my solutions I'm going to have go the same as the solution curves, the space I'm looking in. We'll find that there's a problem with that, and we might need to adapt some things. And let's see which solution curve. Oops, I need to show that solution curve. Right? So I've turned on solution 1, and I've turned on the plot for solution 1. And there I have a plot coming through. Notice it falls steeply because these are very steep direction fields in the negative direction, and then it comes up over here and moves through. Sorry for my mail noise here. And so now I can explore some things happening. In fact, I'm seeing different behavior at different points here. I'm kind of dividing the space into quadrants where things happening in the first quadrant are different than things happening in the second quadrant and third quadrant. In fact, over here it looks like everything falls towards this line, right, of x equals 1 rather quickly, and over here everything rises towards that line of x equals 1 rather quickly. And so I can explore those different spaces, but what interests me is what's happening here in the middle. So I think I'm going to look from negative 1.5 to positive 1.5, right, because I want to look at what's happening here. Notice again, I'm not really answering a question, I'm exploring what can happen. So I'm going to come back and I'm going to change this to negative 1.5 and this to positive 1.5, and change this to negative 1.5 and this to positive 1.5. I might need to change my step size, but let's see what we get. Oh, I missed something somewhere. Negative 1.5 to positive 1.5. My direction field is off a bit. So what did I do differently? Negative 1.5, 1.5, 20, 20. What turned off? Looks like in my graph I am not showing the full range. So let's see, I have 101 steps here. I started, oh, what happened is I started well above 2.5, right? And I said I wanted to only look between 1.5 and 1.5. So where that equation started was outside of my range, and so it added the extra stuff in. And if I pull that back down, I've got my solution curve. Now notice there, I made some mistakes. I went back and checked them, but I used working code to help me explore my space. So let's turn on another solution. I'll turn on solution 2, and I want to see what happens at negative, if I start at negative 1 negative 1.5. And I'll turn on solution 2, and I'll turn on the output for solution 2. And so now we have behaviors, and I'm exploring behaviors and seeing what this function does. And this is going to be a good thing. Even when you do the analytical solutions, you can come back to here and you can see if your solutions are matching the behaviors you see. And if you're in a real-world situation modeling, you can look at what your solutions are going to look like. So I have this code in its first iteration up here running, and you can just use this to modify different solutions and play with things. You don't have to rewrite code every time you do a differential equation now.